So 2 by 2, we're talking about equations that have two unknowns. So we can rewrite them as y equals mx plus b. That tells us it's a straight line. The highest power that x is raised to is 1, and there's two unknowns, therefore we're dealing with straight lines. There are only three options we can have. It could be the case that those lines, those straight lines, intersect at a point, and that's usually the case. Chances are that there's nothing funny going on with these lines, and somewhere they are going to intersect. The point of intersection is an xy coordinate, and that is the solution that we're looking for. When we're solving these equations, we're working to find that intersection point. Of course, the point where they intersect means that that xy point lies on both lines, so we'll also want to check it. Rarer situations are if those two lines are parallel. They cross the y-axis at different points, so they have different y-intercepts and frankly different x-intercepts, but they will never cross paths, so there are no solutions here. So if the lines are parallel, we say that we have an inconsistent system and there is no solution. You'll see that wording used interchangeably. Finally, what if those two lines lie one on top of the other? They're kind of the same line. We say the lines are coincident and it's a dependent system where, since every point on the first line also lies on the second line, we have an infinite number of solutions. So we very briefly, well, it was a little tedious, I know, looked at this graphically, but we also looked at this algebraically. Just as a refresher for, again, algebraically, we'll have an xy coordinate. Even if x is equal to 0 and maybe even y is equal to 0, even if we have both, those are valid numbers. So we have an xy coordinate where the lines intersect. If, however, as we're solving a 2 by 2 system algebraically, and we get to the point where we find that 0 equals some number, let's say 4 or -6, well, we know that's not true. So if we have a nonsense statement like this, you'll notice there are no x's or y's, right? There's no x or y in this expression. It's not the same as having x equals 0, y equals 0. That would be a perfectly valid point. But this statement, patently false. So that tells you that you have parallel lines. You've managed to eliminate both your x's and your y's when you added the two systems together. Or maybe you've eliminated the x's and the y's while using this the method of substitution. And then finally, if you eliminate both the x's and the y's from your equation, but at least you have a true statement, 0 equals 0, that's how you know that those lines were actually identical, which makes sense. If I take one line and any quantity, in this case it happens to be a function, and subtract an identical thing from it, I have nothing left. 0 equals 0, it's gone. So those were the three scenarios we were looking for. Well, instead of being straight lines on an x, y coordinate plane, these are on an x, y, and z axis. So z would be perpendicular to all the others, right? So it would be coming towards you and going back in. So it's at 90 degrees to the y-axis and at 90 degrees from the x-axis. So now we're talking about essentially a line in 3 dimensions. So each of these equations represents a plane. Think a piece of paper that extends in all directions. So now we're looking for a single intersection point where the 3 planes meet. Sometimes they're not all planes. It's only a plane if I in fact have an x, a y, and a z. And we certainly have equations where we have some planes and some straight lines, some linear functions. In any case, we're looking for the single point where they all connect. You could absolutely have the situation with these ones where you've got parallel planes, or 2 of the planes are parallel, one of them crosses through. The planes can intersect at a single point, or maybe they intersect along a line, or maybe 3 planes don't all intersect with each other, only with some pieces. The only situations that we're going to look at are the situation where you have a single x, y, z coordinate where the 3 planes intersect. Some of the questions on the review may have the situation where the planes are parallel or the planes are the same, they're coincident. So they're a dependent system, and the rules there are the same. When you have nonsense, 0 equals a number, Well, then you know you have parallel planes. When you have 0 equals 0, you know that you have at least, you have whichever two planes you're looking at, you know that those two planes are the same. But for the purposes of the test, we will have a solution. What do those look like? So again, we have the strategy written out, but we'll go over that strategy by doing it. Okay. So we have three equations, and this, I actually prefer to start with a system of three equations and three unknowns, where each of the three, in this case planes, each of the three pieces does have each variable. The next question I know looks trickier because one of the equations is missing one of the variables, but it's actually an easier question to answer. I just see more errors with it. So we're going to start with one that has all three unknowns in each of the three equations. And I'll number them 1, 2, 3 with circles around them so that I have something to refer to them by. So equation 1, equation 2, and equation 3. This is just a shorthand for it. Here's the strategy. We're going to take two of those equations, any two, and we're going to eliminate one of the variables, either the x, the y, or the z. Okay? Any two equations eliminate one of the variables. Separately, you're going to take a second pair. So for example, if you take equation 1 and 2 and eliminate the x, you could now take equation 2 and 3. And you're also going to eliminate the same variable. So if you took equation 1 and 2 and eliminated the x, you now take equation 2 and 3 and make sure you also eliminate the x. What does that create? Well, it creates two new equations, two brand new equations that have only two unknowns. How do you solve a system of two equations and two unknowns? That's what we spent Friday doing. So you already know how to do that. So we're essentially using the same technique iteratively. And in fact, if you can solve a 3x3 system, you can solve a 4x4 system using exactly the same technique, just cutting out variables. All right, so what would we like to do? Out of the x's, the y's, and the z's, which one would you like to eliminate? Well, when I'm thinking about it, I'm thinking about what the easiest way would be to eliminate it. So I see, for example, that in equation 1 and 2, I have a positive 1y and a negative 1y. So if I add equation 1 and 2 together, I immediately eliminate the y. I didn't even have to multiply one or both of the equations by a constant. I can just add them together and eliminate it. Furthermore, so that would be using 1 and 2. I can then use 2 and 3 because I've got a negative 1y and a positive 1y, add those two together, so that's a different pair, and also eliminate the y. Similarly, you could take equation 1 and 3 and eliminate the y, but because they have the same sign, you'd have to use subtraction, and we know we make more errors when we do subtraction, so we generally try to avoid it. All right, so I'll take equation 1 and 2 and add those together. Equation 1 and equation 2. So here's my shorthand for what's about to happen. So I won't rewrite the equations, I'll just do the addition. So the x's, the y's, and z's are already lined up, so we can just add them as given. So x plus x is 2x. Positive y plus negative y is 0. So we have eliminated the y. Z plus 2z is 3z. And finally, negative 2 and negative 5 give negative 7. And I'll call that equation 4. That's our first step. I'm going to keep equation 4 to the side for a moment. It's going in the parking lot. We have our first equation that has two unknowns. Now I need to create a second equation that has the same two unknowns. So even if it would be easier to eliminate the z's, I don't care. I need a second equation that has only x and z, but no y. So an easy way to do this is to take equation 2 and 3. It's a different pair, and it's an easy one where if we add them together, we eliminate y. So let's add equation 2 and 3 together. X plus 3x is 4x. Negative y plus y is 0. Perfect. 2z plus z is 3z. Oh, that's not so bad. And negative 5 and negative 12 give me negative 17. And I'll call that equation 5. So once we're here, our entire focus is now on this system, the 4 and the 5, equation 4 and equation 5. It's a system of equations where I have two equations with two unknowns. Let's use elimination again. In this case, I noticed that I have positive 3z and positive 3z. So what I could do is take equation 4 and subtract equation 5. Or alternately, you could take one of the two equations and multiply through by negative 1 to turn that 3z into a negative 3z. Remember that the two equations aren't linked in any way. So what you do to equation 4 doesn't have to match what you do to equation 5. The only rule is that whatever you do to the left side of an equation, you have to do to the right side. So you can multiply by any coefficient you choose, as long as you do it to both sides. I think I'm going to break my own rule of preferring to use only addition and show you what subtraction looks like. So just to give myself a little more space, I'm going to rewrite equation 4 and 5 over here. So 2x plus 3z is equal to negative 7. That was equation 4. And then we're going to subtract equation 5. So we're going to subtract 4x, 3z, and negative 17. Here's my straight line. There we go. Okay. So be careful here that you're subtracting every single term. So you have 2x minus 4x is negative 2x. 3z minus 3z is 0. Perfect. And negative 7 minus negative 17 is negative 7 plus 17. So we have positive 10. Dividing both sides by negative 2 isolates the x, and we find that x is equal to negative 5. All right, so x is equal to negative 5. We have one of our unknowns. Fantastic. How do we get a second unknown? How do we solve for a second one? Well, if I take x is equal to negative 5 and I put it directly into one of the original three equations, let's say I substitute the 5 in for x in equation 1, well, I still have two unknowns. I still have a y and a z. So that's not the ideal way to do it. So instead of substituting it back into the original equations, I'm going to take the x equals 5 and substitute it into any of the equations that has only two unknowns. So I'm going to say, let's substitute x is equal to negative 5 into equation 4. So I have 2 times negative 5. 2 times negative 5 plus 3 times z is equal to negative 7. So I have negative 10 plus 3z is equal to negative 7. 3z is equal to, I'm going to add 10 to both sides. So I have positive 3, so z is in fact equal to 1. Beauty. Now that I know x and I know z, now you can go back into one of the original three equations. So I'm going to substitute x is equal to negative 5 and z is equal to 1 into equation 1, 2, or 3, and I'm going to choose equation 1. So I have negative 5 plus y plus z, which is 1, is equal to negative 2. So I have y on the left-hand side, but negative 5 plus 1 is negative 4. So we have y minus 4 is equal to negative 2. Adding 4 to both sides gives me y is equal to 2. And there's our final answer. So we find that the x, y, z coordinate where these three planes intersect is, as you've correctly identified, negative 5, 2, and 1. They take a little bit longer, but we really didn't do anything new. We simply added or subtracted equations to eliminate variables. It's an iterative process. This particular question, because it was quite easy to get rid of the y's, didn't involve a ton of work. And then it turned out really nicely that I could simply take equation 4 and 5 and subtract them and then immediately get rid of the z. The next examples we'll see are a little bit more involved, but the process is exactly the same. So one more example where you've got 3 equations, 3 unknowns, and each equation has each unknown. what I'd like you to think about first is which of the three unknowns will you eliminate? You're going to eliminate either the x, the y, or the z in two different ways, using two different equations. I think the z is an easy one to eliminate because I can use 1 and 2 and just go ahead and add them together, and then I lose the z. And then I can get rid of z a second way by using, well, I could use 2 or 3 or 1 and 2. But if I use 2 and 3, I have a negative z and a positive 2z. So if I take equation 2 and multiply through by 2, that would give me a negative 2z. I could then add that to equation 3 and eliminate the z. Equation 1 and equation 2 and add them together. And the goal is to eliminate z. 4x plus 2x is 6x. 2y minus 3y is negative y. Z minus z is 0. Perfect. 24 plus 2 is 26. And I'll call that equation 4. All right, so I have one equation that has x and y, so I need to generate a second equation that has only x and y. This one takes a little bit more preparation. We'll have to take equation 2 and multiply through by 2. So I'm going to take equation 2 and multiply by 2. Having these shorthands, just a little hint as to what you're doing, is fantastic. It makes it easier for you to read through your solution. It makes it a lot easier for me to read through your solution. So it clearly indicates what you've done. See that my pen still freezes up. All right, so I have 2 times 2x's, 4x. 2 times negative 3y is negative 6y. 2 times negative z is negative 2z. And 2 times 2 is 4. Don't forget to multiply both sides of the equation by 2, even though I've only written it over here. So that used to be equation 2, but I've modified it. So I'm going to call that equation 5. I'm going to write equation 3 underneath it. So this is just equation 3. I'm not doing anything to it. So I will continue to call that equation 3. And now I'm going to take those two and I'm going to add them because that will allow me to eliminate the z's. So I should indicate what I'm doing. And again, this is going to be equation 5 plus equation 3. 4x plus 5x is 9x. Negative 6y plus y is negative 5y. Negative 2z plus 2z is 0. And 4 and 20 minus 1 make 25. And I guess I have to call that equation 6. All right. We're at the point that we got to before. We have 6x minus y equals 26. We called that equation 4. And 9x minus 5y equals 25. That was equation 6. We have two equations with two unknowns. Go ahead, eliminate another unknown. I know that if I take equation 4, multiply through by minus 5, with the goal of getting a positive 5y here, I'll have to take 5 and multiply by 26, but you've got a calculator. You don't even have to do it by hand. So don't shy away from slightly larger numbers. So as soon as you have one unknown, I think of this as working backwards, right? We've had a 3 by 3. We went down to a 2 by 2, and we kind of had a 1 by 1, if you want to call it that. So now I'm going to go back up. I'm going to take the fact that x is equal to negative 5, plug it into the 2 by 2. That will allow me to solve for y. And then I'll go right back to the 3 by 3 to solve for z. The answer is most definitely x, y, z is equal to 5, 4, negative 4. How do you know we got this right? Well, remember that when we checked in the 2 by 2 system, and this is a bit of an aside, because I can't ask you to show a check on an online test, but I would have if you were writing this on paper. When you're doing a check, you want to make sure that 5, 4, and negative 4 makes sense for equation 1, but also for equation 2, and also for equation 3. So it's very possible that you try equation 1 and you say, okay, that's 4 times 5 plus 2 times 4 plus negative 4 is equal to 24. And then we find, okay, 20 plus 8 minus 4. Yeah, that's 24. Great. So we know that it is a point on this first plane. It's possible that it's a point on the first plane, but not a point on the other two. So you always, always, always want to check your solution in all three to be sure. I know it's an online test. I won't see it, but as a life skill, this is how you check your answer. So you want to make sure that it works for all of them. Checking it in each one. So we have 5 times 5 plus 4 plus 2 times -4 is equal to 21. Are those actually correct? I hope so. Now, I find this completely understandable, but I promise you that this question is easier, or at the very least, it will take us less time to solve than the previous 2 questions did. Which variable should we eliminate first? There's no wrong answer, but I will tell you that the fastest way to get to the answer is to notice that we already have one equation that's missing a y. This is a weird way to write this equation, right? There's nothing, we don't need to leave that space. There's nothing going on here. It's just a plus 1z is equal to -3. The space is intended to help you, and this is how it's written on the test. So that's why I left it in the example. But what I noticed is I already have one equation that has only x and z. So if you said y, you're exactly right. For the fastest way, not the only way, just the fastest way. If I take equation 1 and equation 3 and also eliminate y, that would very quickly give me a second equation that only has x and z. So let's see how we could do that. Well, to get rid of y, we've got a -y and a positive 5y. So I don't even have to do something to both equations. If I look at 1 and 3, I really only have to take equation 1 and multiply through by 5. Right? So if I multiply equation 1 by 5, so equation 1 times 5, that gives me 5x minus 5y plus 25z is equal, oh my goodness, 17 times 5 is 85, so -85, and I'll call that equation 4. And I'm going to write equation 3 below it. You don't have to rewrite it, but I find it easier to follow if it's separate. Choose your own style here. Now I can take those 2 equations, because I've got a -5y and a positive 5y, and add them together. So I'll take equation 4 and add that to equation 3. So I have 6x plus 26z. That's another one that's easy to miswrite. And 85 minus 7 would be 78. So I have -78. So we have x and z, x and z. You've got a 2x2 system. You know how to solve 2x2 systems. And we should call that equation 5. So if you haven't done it yet, I suggest you ignore me for a moment and solve for x and z. So again, this isn't the case where 0 equals 0. We still have an x. X is allowed to be equal to 0. So don't panic there. There is a solution. And I know that x is equal to 0, so I'll start subbing that in. We do have x is equal to 0, y is equal to 2, and z is equal to -3.